So before I move into this chapter, what we are going to do now from here onwards, we are going to talk more about estimation. How do we estimate an unknown quantity from the population? So suppose that in statistical inference, we wish to learn about one or more than, in this course, probably one, not more than one. We wish to learn about the unknown population parameter. Usual notation for the unknown parameter is theta. For example, mu is unknown, we call it theta. Sigma square, the population variance is unknown. How do we estimate sigma square? Using the sample variance S square. How do we estimate the population mean? Using the sample mean X bar, and so on. So for every unknown parameter theta, there is an estimator called theta hat. Let me call it theta hat. So this theta hat is called the point estimate for the unknown parameter theta. So a point estimation is the process of providing a single numerical value as an estimate to that parameter. We denote it by theta hat. It's computed from the sample. So obviously it's a function of sample. And this final value is called the point estimate. For example, if you get X bar to be 10.7, this 10.7 is the point estimate for what? For the unknown population mean. Now, I'll not use the slides here, though I have the slides here. I'll go to the right of the slides here and explain the concept to you without the slides. Suppose I have a population here. This is the population on a variable X. This population is either discrete or continuous, I don't care. This population is modeled by a probability density function or a probability mass function, f of x. Maybe normal, maybe exponential, maybe binomial, maybe hypergeometric, maybe Poisson, maybe normal, log normal, any distribution. Okay. In that distribution, there are unknown parameters, like for normal, there is mu and sigma. For variable, there is alpha and beta. For log normal, there is theta and omega, and so on. There are unknown parameters. So those unknown parameters, I'm calling them theta, where we are interested to estimate these unknown parameters. Let's say the population mean is unknown, so theta is the population mean. You want to estimate that. Now, to estimate this mean, what do you do? Inside the population here, you have many values of X. Maybe infinite values of X are there inside the population, right? And these values are modeled by a function called f of X, probability density function. For a moment, assume it's a continuous distribution. So it's a density function. And for this density function, the population mean is unknown. Let's say X is the time until next defect exponential. And mean is unknown. How do you estimate the population mean? Mu. Sample. The first thing is you will take a sample from this population. So the first thing you will do is you will take a representative part of that population. What do we call that representative part? We call it sample, right? And this sample will be what? This sample will be values, n values. The size of this sample is what? Small n. Then what do you do with this sample? Find the sample mean, correct? From this sample, you will find X bar, which is the sum of values divided by the number of values. Now let me make it specific. Mu. So the density is a function of population mean. We have that unknown population mean, and to estimate that unknown population mean, we took a sample, and from the sample, we computed the sample mean. Let me make it even more general. And we said that this X bar is a point estimate of the unknown population mean mu. Correct? Correct? This is the whole story. You have a population on a variable X. There are many items inside the population, maybe finite items, maybe infinite number of objects. These objects are modeled by a density function f of x. This density function depends upon some unknown constants, the parameters of distribution, beta, delta, gamma, omega, mu, sigma, whatever. To estimate that unknown parameters, you take a sample from that population, a representative part of the population, and from that sample, you compute the corresponding estimate, point estimate. If sigma square is unknown, you will compute the sample variance. If population median is unknown, you compute the sample median. If population highest value is unknown, you will have some estimator for the highest. Whatever is required from the population, you will compute the corresponding sample estimator for that one. And you will call that thing to be a point estimate of the population parameter. This is all we have done in chapter 6. Correct? We have done all of it in chapter 6, the descriptive statistics. If population interquartile range is unknown, we find the sample interquartile range. If population Q3 is unknown, we find the sample Q3. And so on. Right? Now, the next question is, if I take a sample, imagine this is the population, and I take a sample, and from that sample, I get X bar to be, let's say, 10.4. I will say this 10.4 is a point estimate for the population mean. So I will say my population mean is around 10.4, not exactly 10.4, but I'm confident it will be around 10.4. Now, my question is, if I go back to the same population and pick another sample and compute the sample mean from that second sample, will it be exactly 10.4? Same population. I take the sample from the same population. First question is, will it be the same values? No, there will be the different values. For example, this is my population. First, I pick 3 students and ask them, what was your score in major 1? Note down x1, x2, x3, find x bar. Then I pick another 3 students randomly and ask about major 1 score. So my second sample mean, will it be the same as the first sample mean? Not necessarily. So I will have another value of x bar. Let's say it is 10.1. It will be close to each other, right? Because they are estimating the same quantity. And I keep doing this process, and I keep taking samples. And I take infinite many samples. My question number 1. Is X bar changing from sample to sample? Something that changes, what is it called? Variable. Something that changes is called variable. This means X bar is a variable from sample to sample. Within sample, it's fixed. For a single sample, it is fixed, but now I'm talking about sample to sample. It's a variable. Now, my next question, if I tell you that my first sample gave me a mean of 10.4, and I'm planning to select another sample, can you tell me what will be the next value of X bar before even picking the sample? I told you first sample gave me 10.4. And you tell me what will be the second value? Can you exactly tell me what will be the second X bar? No. If I tell you the first one was 10.4, the second one was 10.1, can you tell me the third one? Can you exactly tell me? Close to, but can you tell me? It is unpredictable, correct? Something which is unpredictable, what do we call it? Random. Merge the two terms together. X bar itself is a random variable. X is a random variable, but X bar is also a random variable. Now, from your knowledge of chapter 3 and 4, we have come to know that every random variable has a distribution. Sometimes it is well known, like binomial, Poisson, Weibull, normal, log normal. Sometimes it is not well known. So we just write down the density function and solve it through the general case. But every random variable has a distribution. What will be the distribution of X bar? Because it is a random variable, of course, it has some distribution. This is the question for whole chapter. Yes. This one. You did not give it any name. Not well known. General case. So the question now is, what will be the distribution of X bar? Yes. Now the answer to this question is, where is X bar coming from? Go backwards. Here is X bar. Where is it coming from? From the sample. Where is sample coming from? The population. How is population modeled? Using this function. So this function is the distribution of X. So ultimately, the distribution of X bar will depend upon the distribution of X, of course, because X bar is coming from X, correct? So whatever is the distribution of X bar, it will depend upon what was the distribution of X. Now here I have two results. The first result, before that result, I will write that one, because X bar is coming from X. This implies distribution of X bar depends on the distribution of X. Now here I have case number one. If my X is normally distributed, then X bar will also be normally distributed. This is the result number one. The mean will be same, the variance will be different. If X is coming from a distribution that we don't know, it's F, not normal. Any other distribution, maybe variable, exponential, whatever, unknown, whatever distribution. What will be the distribution of X bar in that case? We have a theorem in statistics mathematically prove that even then the distribution of X bar will be approximately normal. Even if X is not normal, the distribution of X bar will get closer and closer to normal when N gets larger and larger. And according to the experiments, we see that if N is greater than or equal to 30, this approximation works reasonably well. Reasonably well. So 30 can be considered as a large number for the reference. If the sample size is greater than or equal to 30, the approximation will work well. If it is not greater than 30, the approximation will be less accurate, but still approximation is approximation. Even for greater than 30, it is an approximation, not exact. No, if you don't know the distribution of X, you cannot find exact distribution of X bar. If you know it is weighable, then you can find exact. But here I'm considering to be any distribution other than normal. Unknown, maybe. You don't even know what is the distribution. We'll talk about that one. We'll talk about that one. So let us repeat the whole thing now. For this whole thing, we have this population on the random variable X. This is modeled by a function called f of X, where you have the unknown parameter. You take multiple samples from this population, sample 1, sample 2, sample 3, all the way up to infinite many samples. Each sample is of size n. For each sample, if we compute the statistic, for example, X bar, this statistic itself is a random variable that varies from sample to sample, changes from sample to sample. And then every random variable has an associated probability distribution, sometimes well-known like exponential, weighable, normal, and so on, and sometimes not well-known. This distribution of a statistic, we call it to differentiate it from the distribution of original variable. For the variable, we call it probability distribution. For the estimator, we call it sampling distribution. Just to differentiate the names, the distribution of an estimator is called sampling distribution, and the parent distribution is called probability distribution. So this distribution, we will call it probability distribution, and the distribution of X bar, which we will call it to be normal due to approximation or exact, we will call it sampling distribution. So the distribution of a sample estimator or statistic is called the sampling distribution. Here we have the two results. Result 1 says that if X is exactly normal, X bar will be exactly normal. But if X is not normal, then X bar will be approximately normal for sufficiently large sample size. And this result is based on a theorem called Central Limit Theorem. This Central Limit Theorem says that no matter what is the distribution of X, the distribution of sum tends to normal. Mean is actually a sum divided by a constant number, sum divided by n. So the Central Limit Theorem says that the sum tends to normality as you increase the sample size. Let me quickly show you something. Now that you are used to of R language, I will show you this result quickly in R language.
What if n gets closer to the populations? What happens?
This is the kind of a question where you are putting a question mark on the whole data science. If n is close to infinity, if you have the resources and availability of the whole population, you don't need to take a sample. Then the whole statistics is thrown in the garbage. You don't need statistics if you have the population. Is the font size visible or no? Now, okay, now I will first do what? I will generate some values of X, and I will fix my sample size to be, let's say, 10. And I will generate it from normal distribution. And the mean of normal distribution, I will fix the mean to be 20, and the variance, I will standard deviation, I will fix it to be 2. So this will generate 10 values from a normal distribution. Mean will be 20, standard deviation will be 2. And then I will compute X bar, which is the mean of this X. This will compute X bar. And then I will repeat this process many times. I will take infinite many samples. Every time I will compute X bar, and I will keep saving that X bar. At the end, I will draw the histogram of that X bar to see how it is distributed. And if it's distributed close to the bell shape, I can say it is close to normally distributed. So I will repeat this process. Ten to the power 6 times, 1 million times. Every time I will compute the value of X bar. And at the end, I will draw the histogram of this X bar to see how this X bar is distributed. And the histogram will show where? It will take time. Histogram will show here. Any plot will show in this area. Now look at the histogram. Is it bell-shaped? Yes, it is bell-shaped. What was the sample size? It was 10. Even if it is 2, even if the sample size is 2, this will be bell-shaped. Why? Because X is exactly normal. The result 1 is exact. So X bar will be exactly normal no matter what was the sample size. 1 or 2 or 3 or 4, this is normal, right? So when X is normal, here I'm generating X from where? From normal. So when X is normal, no matter what is the sample size, X bar is exactly normal. Now I'll go to result number 2. I will generate X from, let's say, exponential distribution. I'll keep the sample size small, 2, very small. And try to see what is the distribution of X bar. Histogram of X bar, the distribution of X bar. The distribution of X bar that is finished is what? Is it normal? No way close to normal. No way close to normal, right? See, when I increase the sample size, what happens? From 2, I make it 20. No, I'll go gradually. Make it 10. Keep this distribution in mind. It is heavily skewed to the right. Heavily skewed to the right. And see, when I increase from 2 to 10, it will turn towards more towards symmetric now. Getting closer. Now I'll make it 25. Now this is less skewed as compared to when n was 2. And when I make it 25, you will see it will be even less skewed. And when the sample size goes beyond 30, the parent distribution was a very heavily skewed distribution. Still, your X bar tends closer and closer to normal when n gets closer and closer to infinity. This is called central limit theorem, which says that no matter what was the distribution of X, X bar will tend closer and closer to normal when n gets closer and closer to infinity. And the quantification for a large value is 30. In your book, the quantification is 30. If n is reasonably large, the approximation works reasonably well. Any questions so far? This is all chapter 7. Now we'll dive into the questions. Any questions? By question, I mean examples now. Now, the critical part of this chapter is that this is exactly the same as chapter 4. The only difference is that you will be asked to find the probabilities or percentiles related to sample mean, not related to single value of X. If I give you that X has a normal distribution with mean this and variance this, find the probability that a value will be greater than 10, you use z equals x minus mu divided by sigma, right? If I ask the question about x bar, what will be the standardization? What will be the standardization? Variable minus its mean divided by its standard deviation. What is the standard deviation of this variable? Square root of this variance. Square root of this variance. So if in exam you get a question about x, you will use this formula from the normal distribution. If in exam you get a question about x bar, you will use that formula. That's the only difference. That's the only difference in chapter 7. That's it. Now let us start. This is your example 7.1 in the book. It says that an electronic company manufactures resistors that have a mean resistance of 100. Mu is given. Correct? Mean resistance is 100. And the standard deviation is given to be 10. The distribution of the resistance is normal. So they give you X following a normal distribution. Mean is 100 and the standard deviation is 10. So variance is 10 square. Find the probability, read the question carefully. Find the probability that a sample of 36 resistors will have an average of less than 95.4. What is required? That X bar is less than. What if the question was find the probability that a resistor will have a resistance of less than 95.4? X less than 95.4. So try to understand the difference. You may get these two questions side by side in exam. One asking for the single value, one asking for the mean value. So for this question, X bar, how do we standardize X bar? We know what is the distribution of X bar. When X is normal, bar is normal. And how do you convert normal into standard normal? By subtracting its mean, dividing by its standard deviation. So X bar minus its mean divided by its standard error. 94.5 minus what is the mean? What is sigma? What is n? So this comes out to be probability of z less than calculators. Yesterday, when I was making the slides, I was facing the similar issue. In the slides, you might find this mistake somewhere. I tried to correct it at many places, mixed up 94.5 and 95.4. I think it is minus 1.6, is it? Minus 2.76. Can you find this probability? Just go to the Z table and look at the area less than minus 2.76, and that area minus 2.76 will be on the left side or right side? Left side. So let's go to the left side and highlight minus 2.7 row. What is the area under minus 2.76? 7, 0, 1, 2, 3, 4, 5, and 6. 0.00289. Zero point zero zero two eight nine. Quickly, next question. Find the probability that a random sample of 36 resistors will have an average between 95.4 and 100. What is required? Right? Convert it to Z, or first convert it to CDF. Now convert it to Z. This is probability of Z less than 0 minus probability of Z less than minus 2.76 we got. What is probability of Z less than 0 without going to the table?
1/2.
1/2. Z is symmetric around 0. Half of the area is below 0, half of the area is above 0. So this is 1/2. Minus Z less than minus 2.76, we found it in part 1, 0.00289. So subtract 0.00289 from half and you get the answer. Clear? Next question. Read it. Put your mobiles in the pockets, all of you. Put the mobiles in the pockets and read the question. The question says that find the value below which 95% of the sample means fall. Which percentile? 95th percentile. You have to solve this equation. Probability of X bar less than A equals to 0.95. Same thing. Standardize it, convert it to Z. When you convert it to Z, X bar minus mu divided by sigma over root of N less than A minus mean is 100. Sigma is 10 by 36. This is 0.95. This implies probability of Z less than A minus 100 over 10 by root of 36 equals 0.95. Call it equation 1. Now go to the table and find a value below which the area is 0.95. Go to the Z table, and from Z table, probability of Z less than what is 0.95? Look for 0.95 inside the table. Look at the table. Look at the table and be attentive now. I'm going to give you a very important point. Now, 0.95 is almost right in the middle of these two. Right in the middle of these two. In exam, if you take the value 1.64, will be accepted. If you take 1.65, will be accepted. But the best thing to do is to go right in the middle, right? Because it is in the middle. So the best thing to do is to go in the middle of 1.64 and 1.65. What is in the middle of 1.64 and 1.65? 1.645. So from the table, we have this equation. Now compare this equation with this equation. What do you get? Compare this one with this one. What do we get? A minus 100 over 10 divided by root of 36 equals 1.645. Right? Solve it for A. A will be 100 plus 1.645 times 10 over 6. Something, whatever you get. Read the last part. How would the results first look at this? In the question, we said that the distribution of X is normal. Now, part 4 says that how would the answers of part 1, 2, and 3 would be affected if we did not assume that the distribution was normal? What if the parent distribution was not normal? What would happen to all of these questions? What if this box statement was missing? Same thing, the answers would become approximations, but exactly the same answers and no change in the solution. No change in the solution at all. If X was not normal, still your X bar will be close to normal and you will use exactly the same formula for Z and get exactly the same solutions. But in that case, all of these solutions will become approximations. So here you will say that the probability is approximately 0.00289. The probability is approximately 0.5 minus 0.00289. And the percentile is approximately 100 plus 1.645 times something. So everything will become approximation. Yes. 100 and 17. You will add this word approximately in every question. In multiple choice, no need to add anything. Then it says, now this is a different way of asking question, more tough than previous 4 questions. An electronic company manufactures resistors. They don't tell you what is the distribution of X. They don't give you what is the mean. They don't give you what is the standard deviation. Just tell you that there is an X. A random sample of 36 resistors is taken and the probability of sample mean resistance. Now try to understand the question. Probability of sample mean resistance exceeding the true mean resistance by at least 0.25 is 0.1. Very, very complex statement. What is given? Probability of sample mean resistance, reading the statement and translating it into notation. Probability of sample mean resistance exceeding the true mean resistance by how much? By at least 0.25. This probability is equal to 0.1. Sample mean resistance exceeds the true mean resistance by at least 0.25. This probability is 0.1. Standardize and get the value of sigma. You will get the value of sigma. So let us standardize. How do we standardize X bar? X bar minus mu sigma over root of n, mu plus 0.25 minus mu divided by sigma over root of n, and this is 0.1. Correct? So the left side becomes Z, mu cancels with mu, n is given to be 36. Let me write 36 here. So it becomes 6 times 0.25 is what? 1.5? 1.5 over sigma, this is 0.1. You got the equation. If the upper tail area is 0.1, what will be the lower tail area? If greater than is 0.1, what will be less than? Because to go to the Z table, you need less than. 0.9. So probability of Z less than 1.5 over sigma will be 0.9. Now go to the Z table and look for 0.9. Where is 0.9000000? Again, you will not find it exactly, but where is it? I think it's closest to this value. So I will take 1.28. So from the table, I have probability of Z less than 1.28, almost 0.9. Compare this with this. What do we get? 1.5 over sigma equals 1.28. So sigma is 1.5 over 1.28. Get the value of sigma.
Feeling the true mean.
It is more than mu. True mean is mu. It is more than mu by at least 0.25. 1.1719. Another way of asking the same question. An electronic company manufactures the resistor. Sigma is given to be 10. Mu is not given. A random sample of size 36 is taken and the probability of X bar greater than this value is 0.975. We are given that X follows a distribution with mu and sigma equals 10 and n is equal to 36, and we are given that X bar being greater than 81.7333, this is 0.975, and we have to find what? Mu. Again, standardize. Probability of X bar, let me directly write it, Z greater than 81.7333 minus mu divided by sigma is 10. Sample size is 36. This is 0.975. Can you go get the probability greater than probability from the Z table? No. If the greater than is 0.975, less than will be what? Now go to the Z table. From the table, you will have probability of Z less than minus 1.96 equals to this one. Compare the two. And from this equation, you will get what? Put 81.73 minus mu over 10 over 6 equals minus 1.28, and you will get the value of mu. This is question 4.1 that you did in chapter 4. Okay. Now I'm turning towards other cases when the distribution of X is not normal. We give you that this is the distribution of X. Let the continuous random variable X denote the current measurement between 4.9 and 5.1. The distribution of X is given. It's not a well-known distribution. A sample of 30 copper wires is taken. What is the probability that the sample mean will be less than 4.99? You are supposed to find the probability of X bar less than 4.99. How will you find this probability? Again, standardize it. Any question about X bar, you will use this. Standardize it. Probability of Z less than 4.99 minus mu divided by sigma over root of 30. Where will the mu and sigma come from? Mu and sigma are the mean and standard deviation of X. Where will they come from? We gave you the PDF, find the mean and variance. You did that in chapter 4, not CDF. Mu is integration from 4.9 to 5.1 x times 5 dx. Sigma equals expected value of X square minus expected value of X whole square. Find them the way you found it in chapter 4. Okay, find them, plug them in here and solve the question. This is the case where the distribution is given but not a well-known. Another case where we give you the distribution and the distribution is well known. What is the distribution? Assume that the lifetime of bearing follows a Weibull distribution. This is question 4.23 from chapter 4. It follows a Weibull distribution. We took a random sample of 30 bearings. What is the probability that the mean is greater than 8,000? Go. This is just 1 minute and you can go now. What is the probability X bar is greater than? Again, standardize it. Z more than 8,000 minus mu divided by sigma over root of 30. Where will the mu and sigma come from? Equations of Weibull are given in the formula sheet. The mu of Weibull is a function of beta and delta. Sigma of Weibull is a function of beta and delta. So go to the formula sheet, get the value of mu and sigma from there, plug it in. Again, the question goes to Z, go to the normal table and solve it. So this is the end of chapter. We did examples and everything. Next class, I will start chapter 8 probably.